Welcome, ladies and gentlemen. Today I want to tell you again a bit about one of the PCBs I built in the last year, or I designed and built in the last year. In one of my former videos I already showed you this PCB. It's called the ButtonBoard PCB. Probably you get directly why this is called ButtonBoard, because of all the buttons on the board. And when I started with this PCB, my intention was to create a simple and individually configurable IoT device that I can use to control the different functions in my smart home. Basically, I wanted to have a simple remote that helps me to trigger actions like light on, light off, heater on, heater off, whatever you can imagine. And what I missed here was a device that is compact, has a lot of functionality, a lot of buttons, and is also freely configurable, because, as you know, I like to have it customized as most as possible for my specific use case. And therefore I started with the ButtonBoard PCB that very soon showed me that I can use this button boards also for other use cases, but on this I will tell you later. First I want to show you what this PCB is about. As you may already see, I decided to use the typical remote layout. So when I get my TV remote, you directly see that it was inspired by these typical remotes, because this is a pretty cool design to use the button board as a typical remote. Therefore I designed it this way, that I have 12 buttons at the top where I can put some main triggers on. These are the 12 red buttons. Additionally, I have 4 side buttons on this side and on this side that remind me a bit about these volume buttons you know from your smartphone. In the end, we were 16 buttons because I wanted to use all the GPIOs of the GPIO bridge here. This is a PCF8575. It's an I2C GPIO extender. So it connects to your MCU via I2C and gives you the possibility to control or read up to 16 GPIOs. And these GPIOs are wired to the different buttons, so if somebody pushes the buttons, the PCF detects it and sends it via I2C to the ESP32. That was the main idea. But one big problem with the ESP32 I can show you is on the other side. I will also tell you more about all the components here later. One of the big problems with the ESP32 is that I have a very huge power consumption for a battery power device. That's not only the fault of the ESP32, mainly also because of design issues with the Wi-Fi standard. So Wi-Fi was initially not designed to use it for battery power devices. So you cannot do much about it, that it uses that much power. But to save as much energy as possible, we use a trick here that is commonly known to put the ESP32 into power down when it's not used. The problem is here again that when I want to use the remote and the ESP32 powers up, it needs some time to powers up, initialize everything, connect to the Wi-Fi, connect to the MQTT server or whatever server you have behind. And that's a pretty annoying delay when you want to trigger some actions fast. Because when you put up a remote, you want to switch on the light, you want to switch on the light now, and you don't want to wait 5 seconds. This delay was one of the reasons why I put the ADXL345 on the PCB. That's here visible. That's a simple accelerometer, so it can measure accelerations in any direction. So there's 3 directions, but of course detects all of them. And communicates the absolute value via I2C bus again to the ESP32. But it has also 2 interrupt pins that you can program and connect to your MCU. And I used this feature on this PCB to detect movements and to already use these movements to wake up the ESP32. So the idea behind this was that normally when you use a remote, pick it up and you push a button, and now the ESP32 starts to wake up, connects to your Wi-Fi, connects to your MQTT server. This takes some time. And I wanted to shorten up this time by using the interrupt feature of the accelerometer. So as soon as I take up the remote and I want to do something, the accelerometer already detects this movement and sends a pulse to the ESP32 on the back that wakes it up. So the ESP32 is not waking up when I push the button, it's already waking up as soon as I touch the remote. So that gives you, I don't know, probably 1 second of time saving, or like felt time saving for the user to have the remote up as fast as possible. Another idea to reduce this sleep time as much as possible, or this boot up time as much as possible, is to use the integrated capacitive sensor of the ESP32. So the ESP32 has on some GPIOs the possibility to detect capacitive changes. You already know this sensor, for example, from your smartphone display, you are able to detect the finger before it already touches the display. And the ESP32 can do something similar. You only have to place an electrode on the inside of the housing. As soon as you touch the housing from the inside at the location of the electrode, the ESP32 detects it and wakes up automatically. These are the two features I want to use to save some boot time, or some felt boot time for the user, that the ESP32 is faster available for controlling your smart home or IoT device or whatever you want to do with it. Also for the remote use case, I placed some WS2812 LEDs here at the side of the buttons. It's the little version, just 2 by 2 millimeters each. So by 12 buttons, it's 24 LEDs. That gives you some multiple use cases. You can use these buttons to illuminate your remote when it's dark. You can use it to confirm the push of a button. So in case you push the button, it's shortly lit up, so you know, okay, I triggered the functionality. You can also use it to display simple data, like, I don't know, battery level of the device or whatever you can imagine here. You have full possibility to use these LEDs to control and to show data or make a simple animation, whatever you like. The other part at the top of the PCB is a little voltage divider here, so that you can connect an LDR, so that's a light depending resistor, in case you want to detect the brightness around the remote. Additionally, this is a part of a voltage divider to detect the battery voltage. That's not perfect right now because, as you know, the voltage curve of a lithium-ion battery is not that linear, but it's enough to have a rough estimation about how much juice is left in the battery. On the other part of the PCB, so you already saw that this PCB is somehow divided into two parts. This is here the button part, and this is the, call it power part, power and communication part, because it has all the stuff we need for powering the device. It has the USB-C connector, again with a fuse, a little SMD fuse, the CH340G that you use for communication with the ESP32. This is a component you probably know from most of the Arduino clones. It's a simple USB to serial bridge. So on the computer side, on the host side of the USB-C port, it emulates a serial device and connects on the serial side to the ESP32 like a serial device. So this way you are able to program your ESP32 and also to communicate with it. So far to this side of the PCB. The other side has some bigger components, but also useful. We have the main MCU, that's the ESP32 here at the top. We have a not populated micro SD card port, so here you can also put a micro SD card in if you want to save or read whatever data. We have 3 quick ports. These ports are extension ports introduced by SparkFun. Basically, it's used to connect additional I2C sensors or actuators to your PCB. So again, my example PCB. Here a simple BME 280 connected to a quick compatible port. You connect it to your device, and right now the BME 280 should be visible on the I2C bus of the ESP32. Yeah, with this you can easily extend the functionality of the PCB with whatever sensors or actuators you like. For future revisions I already turned them around, so from the next revision on these sockets will point in that direction, so you will put in the cable from here, because this way of course you're colliding with the housing part or whatever, if you have a housing part, and that's something I want to avoid. These little things here are the pull-up resistors actually for the buttons. Sad thing, I had to learn that the PSF 8575 does not have any internal pull-down or pull-up resistors, so you have to add them externally. That's why I did here. And this one, the big brown button cell holders, again the backup power for the DS3232M real-time clock. Why there is a real-time clock on a remote, I will also tell you later. First I want to show you the components on the small part of the B, the power PCB. This is basically all the basic circuit you need to power the remote with a lithium-ion battery or lithium polymer battery. We have under voltage, over voltage detection that are, I think this is the MOSFET, the low side MOSFET, to cut off the battery in case there's something wrong with the input voltage or the battery voltage, whatever. Also overcurrent detection, very important. And this is an MCP charge IC, so it cares about the charging of the lithium battery that I have not inserted here right now. But basically this is all the circuit you need to have a basic functionality to interface your circuit with battery power. This is also charged again via this USB-C port. So later when all these parts are integrated into a housing, you just plug it in with your phone charger, whatever cable you have, and then you can charge the remote again. Yeah, that also brings me to my first prototype of a simple remote housing. I've prepared something. So that looks like this. Here again, that's of course another example, not completely populated, just screwed it in to show you how it looks like, the first prototype. Here I have a case that not only contains the button location, so here I have these little knobs I can push, and it of course pushes the button on the PCB in the inside. But I also have an OLED display at the top, so you can also display data. This OLED is connected via the quick connector. It will go in here where the connectors are not populated yet. And this way you have access, or the ESP32 has access to the OLED and can display, for example, the heater temperature. So if you want to use the top two buttons to increase or decrease the temperature in your living room, you can push it up and it shows you heater is now at 22 degrees, whatever you like. Also it has access at the side to the side buttons. There are no knobs inside yet, and also the buttons are not populated on this PCB, but I think it's enough to get the idea. So this is, from my point of view, a perfect use case to probably control the volume of your smart home, stereo, whatever you have there, Spotify, iTunes, all these devices that are connected to your Wi-Fi. And for the back plane, I also prepared two things right now, because of course that's not enough. We need a back part that goes in this way. This is a smaller version, so we are in a similar size, a bit below the width of a TV remote, so pretty handy, or still pretty handy. This is perfect for one of the standard LiPos. I don't know the number, I will put it in the section below the video. So you can put a standard lithium battery here in this section, connected to the solder pads, and you're good to go. Put it on, have the screw holes here, M2 screws, and you can close it and everything is fixed in one compact housing. Or in case you want to have more power, you can use an alternative backplane, that is this one. You already see when you put them side by side that the left one is a bit wider, a bit deeper. That makes the remote a bit more bulky. Not that crazy that you don't want to use it, because from my point of view, compared to a TV remote that you use every day, it's still pretty okay. Advantage of this is that you can use a much bigger battery. So if I remember right, here there goes a 1000 milliamp hour batteries. This one is a 3000 milliamp hours battery. So this housing gives you 3 times of the power that you have with this housing. It's both not that critical because mostly you will use it at home, so you have the possibility to recharge it by time, but yeah, you have some more options to choose how you want to build your button board. One thing I forgot to tell you is the reason for the DS3232M. That is the little RTC chip on here combined with the button cell holder on the other side. A real-time clock gives you the possibility to track time even when the device is not powered. So you save the time here in this device, and in case there's no battery power available or the USB-C connection is disconnected, it will use the energy from the button cell to maintain the time. So after the device powers up again, the ESP32 can connect to the DS3232M, ask him, hey guy, what's the time? And he says, yeah, it's, I don't know, 11:15. And this is of course not needed for a remote because, at least I cannot imagine that there's a use case right now. But that brings me directly to the other use case of this board. Because you already saw that I can break it off here and then I have only this part left. And of course the other part left. And when I separated these two parts, I can also use the button board part to use it as a control interface for other devices. For example, I don't have to integrate it in a remote housing. I can integrate it in a device housing of, I don't know, whatever device you have, and then use these buttons to control the actual functionality of the main device. You still have the possibility to put the USB-C part somewhere else, connected via these solder pads, and then you can also distribute easily power from here to whatever device you have. Yeah, that's the other use case. That was a bit abstract, but I prepared another video to show you this better in one of my other projects. We'll put that in the section below or link directly in the video, we will see later. That's so far about this revision of the ButtonBoard PCB. I'm already working on a new one with some new features, but more on this in another video. So far, I hope you liked it. If yes, please leave me a comment. If not, please leave me a comment as well, but tell me what I should do better. And have a nice day. Bye.